Download this code from codegive.com, link in the description below. Dijkstra's algorithm is a popular algorithm used for finding the shortest path from a starting node, source, to all other nodes in a weighted graph. It works on graphs with non-negative weights and is widely used in various applications such as GPS navigation systems. Key concepts. 1. Graph representation. A graph can be represented using an adjacency list or an adjacency matrix. Dijkstra's algorithm typically uses an adjacency list. 2. Priority queue. A priority queue is used to efficiently retrieve the next node with the smallest tentative distance. 3. Tentative distance. This is the shortest known distance from the source to a particular node. Steps of Dijkstra's algorithm. 1. Initialization. Set the distance to the source node to 0 and all other nodes to infinity. Mark all nodes as unvisited. Create a priority queue and add the source node. 2. Visit nodes. While there are unvisited nodes, select the node with the smallest tentative distance from the priority queue. For the current node, consider its unvisited neighbors and calculate their tentative distances through the current node. If the calculated distance of a neighboring node is less than its current tentative distance, update it. Mark the current node as visited. 3. Repeat. Continue the process until all nodes have been visited or the shortest path to the destination node has been found. Example. Let's consider the following indirect graph. Adjacency list representation. Dijkstra's algorithm implementation. Here is a Python implementation of Dijkstra's algorithm. Explanation of code. 1. Graph representation. The graph is defined as a dictionary where keys are node names and values are lists of tuples representing edges and their weights. 2. Initialization. We initialize distances to infinity and set the distance to the start node to 0. 3. Priority queue. We use Python's heap to maintain a priority queue of nodes to be explored based on their tentative distances. 4. Main loop. We continually pop nodes from the priority queue, explore their neighbors, and update distances if we find a shorter path. 5. Output. The final distances from the source node to all other nodes are printed. Output. When you run the above code, you should see the shortest paths from node A. This output indicates that the shortest path from A to B is 1. The shortest path from A to C is 3, via B. The shortest path from A to D is 3, via B or C. Conclusion. Dijkstra's algorithm is efficient and straightforward for finding the shortest paths in weighted graphs. Remember, it only works with graphs that have non-negative weights. In cases where negative weights are present, consider using the Bellman-Ford algorithm instead.